So far, we have discussed that in previous lectures, we have discussed that how deflecting torque will be generated in that induction energy meter. Now, in this video, we will see that how that braking torque will be developed in that energy meter. Okay, that is braking torque in energy meter. Braking torque in a energy meter. So we will see that how that braking torque that brake magnet and all these things will be there in an energy meter. So basically we are going to have this aluminum disc, okay, like this, and over this aluminum disc we are going to have that braking magnet like this. It is a permanent magnet, okay, it is a permanent magnet. It is a brake magnet. Brake magnet, and it is a permanent magnet, and this is going to have one this is north pole and this is south pole of that magnet, and it is going to produce a flux, DC flux from north to south. It is traveling like this, and which is cutting that disc, okay, and this is a DC flux, okay, and this is nothing but that disc, okay. Now because of that deflecting torque, the disc is going to rotate, okay. Because of that deflecting torque, the disc is going to rotate. What is that deflecting torque we have got? That is RMS value of series flux into that RMS value of shunt flux into sine of beta and cos alpha. That is nothing but that deflecting torque. Because of that deflecting torque, this disc is going to rotate. Now what happens is that when disc rotating in that flux produced by that brake magnet, then an EMF will be induced in this disc. Because of that we can imagine that disc as a conductor, and that conductor is moving in that this flux, whatever this flux is there. That is an motional EMF which is similar to that BLV. Now then this EMF in this disc will produce eddy currents in the disc. Eddy currents in the disc, okay, that is what. So when disc rotating in the flux produced by brake magnet, then EMF induced in disc, okay, this is nothing but that motional EMF, okay, which will be similar to BLV, okay. What then? This EMF produces eddy currents in disc, because the disc is having many short circuit paths on it, so it will be, okay, we already know about that eddy current paths, okay. Now what happening is that now this disc is going to have an eddy currents because of this what flux. Why that eddy currents is coming? That eddy currents is coming because of that relative motion between that disk and this flux. Now, according to the Lenz law, what it says, the effect will oppose the cause. So now this eddy currents induced in that disk will oppose that motion of that disk because of that Lenz law. That is what an Lenz law says. So then the disk will stop. So there is an opposition to that disk. There is an opposition to the disk. This is what basically that how braking torque is developed in that braking torque will be developed in that disk. That means there is an opposition to that motion of the disk because of that Lenz law. Opposition means it is opposing in opposite to that direction of that deflecting torque. So opposite to the motion of that disk. Okay. Suppose if the disk is rotating clockwise direction, then opposition will be there anti-clockwise direction. This is an opposition, and this disk rotation. Okay, that is the thing. Okay, that is what it is saying. That now apply that Lenz law. What it is saying, that effect opposes the cause. That is, cause for EMF production is motion of disk. Okay, so induced EMF or eddy current in where? The disk. In a disk. Okay, in a disk opposes the motion of disk. Okay, such that opposing or controlling torque. Okay, controlling torque or brake torque produced on a disk. Now this the EMF that is induced on that disk because of this DC flux or brake magnetic flux is given will be proportional to that E will be proportional to phi and N. Phi and N, because similar to that BLV. Okay, and now we can write that E as E is equal to K1 phi into N, where phi is the flux produced by brake magnet, and N is nothing but speed of disk. Here flux means that is number of lines of flux. Okay, now similarly the eddy currents in the disk, eddy currents in the disk will be given by I is equal to E by R. Okay, okay. Now this R is nothing but resistance of disk, resistance of disk. Why here impedance is not taken? Because here this is an DC voltage. Now for DC that reactance will be 0 because frequency 0, XL is equal to 2 pi FL, that 0. It acts, that inductance will act as a short circuit. Now substituting that value of E here, it will be equal to K1 phi N divided by R. This is about that eddy current here induced in this thing. Okay. Now the braking torque that is developed on the disk will be that brake torque will be directly proportional to that flux of that brake magnet into current, eddy current induced in the disk into that radius of that disk. So radius of the disk means here we are going to have that disk, no, and here we are going to have that axis of that disk. This is nothing but that radius. Okay, that is that radius of that disk. So we need to by heart this expression, similar to F is equal to BIL sin theta, BIL. In the same way this also. Okay, what to say, similar to BIL. Okay, that is the thing. Okay, that is the thing. So this brake torque is nothing but it is the interaction due to brake magnet flux and eddy current in disk, eddy current in a disk. Okay, now that braking torque TB will be proportional to phi I and R, and that TB will be can be written as one constant proportionality. You take this K2 into I, phi and R. Okay, now substitute that value of I in the above equation, then TB will be equal to K2 phi, and substitute that value of I as K phi N divided by small r into capital R. Now this expression for braking torque TB will be equal to K1 K2 phi square N divided by R into capital R. So what we can say, that TB is there, no, that TB will be proportional to phi square N and R, and it is nothing but capital R. This is that braking torque expression, very important. This is very important. Okay, remember this expression. Now let us say if that radius of the disk is constant, it will not change once that energy meter is designed, then you can write this TB will be proportional to phi square N and R. Now add one constant proportionality to this thing, TB will be equal to K3 phi square N divided by R. Okay. Now here say this N to be equal to N, which is nothing but speed of disk, say, but speed of disk, speed of that disk. Then TB will be equal to K3 phi square N and R. Here phi is nothing but what is the flux produced by brake magnet, where R is nothing but resistance of disk. Okay, this is the thing we have to observe. Now let us take that ideal case. Let us take that ideal case. Okay. Under steady state condition, that a deflecting torque developed in that what to say in brake in a disk average value will be equal to that braking torque developed in that disk. Both are equal under steady state condition. But okay, but we have got this for an ideal case, this TD net average. We have got this value as an constant K into power. Okay, and which will be equal to this TB is nothing but how much K3, it will be phi square N and R. Okay, that is power. Okay, this power will be directly proportional to that speed of disk. Okay, speed of disk, that is, this is the power in the circuit, that is power in circuit or load. The expression for this power will be VL IL and cos phi. Already we have seen in that deflecting torque equation this expression. Now total number of revolutions will be equal to this K into integral N dot dt. This is an equation, you have to remember this thing. And previously what we have got, that N, so that N we have got it as a constant K into that power. No, whatever that K is there, I have written here only. So N we have got it is an K into power. So this is nothing but power into dt. Okay, here this power is nothing but VL IL cos phi, where phi is the angle between that VL phasor and IL phasor. This is the load, whatever that load is there. Now we are connected to that energy meter, that is this one, VL and IL. Okay, that is for an ideal case. you can say that this will be equal to k, whatever this part is there, no, that is energy consumed by that load. Energy, okay, energy, okay, that is for ideal case, total number of revolutions in disk will be equal to k into ER, energy. So now this energy unit will be kilowatt hour. Now this will be revolutions. So now this units of this one will be revolutions per kilowatt hour. Okay, revolutions per kilowatt hour. So in an energy meter, for an ideal case, the total number of revolutions made by the disk will be equal to k times of that energy consumed by that load. This is the one of the important thing we have to observe. This energy is nothing but integral power into dt. Okay, this is that. This is the observation we have to keep it in mind every time. Okay, this is the observation you have to keep it in every time. Now we will see that a non-ideal case. In non-ideal case, or it is in practical case, that TD net average what we have got will be proportional to that VL IL, and it is nothing but sine of delta minus phi. This thing we have got for a non-ideal case. Now this can be written as that TD net average will be equal to some constant k into VL IL sine of delta minus phi. This thing we have got in the derivation of that deflection torque of energy meter. There we have got. Now under steady state condition, this TD net average will be equal to TB, whatever that breaking torque is there. Now this will be k into VL IL sine of delta minus phi will be equal to that k3 into phi square n divided by r. This is this equation. Okay, now what we have got is that that speed of disk n will be proportional to this VL IL sine of delta minus phi. Okay, and now this thing we can write it as n equal to k times of VL IL sine of delta minus phi. This thing we can write. Now the number of revolutions made by the disk, number of revolutions by disk will be equal to integral n into dt. Now substitute this n equation here. It will be getting as in k into integral mod VL is an IL sine of delta minus phi into dt. This is not that true energy. True energy consumed by load, not the true energy consumed by the load. That is here, that is here, that delta is not equal to 90 degrees. Okay, this is the error due to pressure coil or shunt coil resistance. Shunt coil resistance, shunt coil resistance. Okay, shunt coil resistance. Now if that rp is equal to 0, that is the resistance of that shunt coil is 0, then delta, which will be equal to that tan inverse of that xp divided by rp, will be equal to 90 degrees. Then number of revolutions will be equal to k times of energy consumed by load. This is an ideal case. This is ideal case only if rp is 0. That is, so what we have to observe is that, so we need to remove the error due to pressure coil or shunt coil resistance in order to get the true energy read by the energy meter. So we need to remove the error due to pressure coil or that shunt coil resistance in order to get the true energy read by meter. Okay, this is all about that braking torque developed in that energy meter. Okay, this is the thing. Thank you.